All right, this video is on spectrophotometry. And to really understand how this works, first we're going to talk about how light works and what light is, and then we're going to talk about how light interacts with matter, and atoms, and electrons, and molecules. And then we'll take a look at how a spectrophotometer, the actual machine, works and how it's used. And then we'll look at how we can get from the absorbance of light to actual measurements of concentration. So light travels in waves, and one of the best ways we have of quantifying light is in wavelengths. So the wavelength is simply the distance from the crest of one wave to the crest of the next wave, and it's usually symbolized as the Greek letter lambda. Not all wavelengths are the same for light. It comes in a wide range of wavelengths, as you can see from the spectrum here. On the far left, we have wavelengths that are on the scale of individual atoms or smaller. And on the far right, and this actually in reality extends farther than this, you have wavelengths here of 100 meters. That's a football field between the crest of one wave and the crest of the next wave. But this actually extends out into kilometers, so on the scale of miles. Long wavelengths have less energy than short wavelengths. So if we look at the spectrum here, and it's labeled with the different types of electromagnetic radiation. You have long wavelengths are often referred to as radio wavelengths, AM, FM, TV, cell phone, microwaves. Um, and then you get into the infrared, the ultraviolet, X-rays, and gamma rays. And I think with just a thought experiment here, you can see the difference in energy. If you hold your hand under a heat lamp, for example, let's say you're at a buffet and you're reaching for a chicken wing, you will feel the infrared radiation on your hand as heat, but it won't do any damage. If you hold your hand under an ultraviolet light for any period of time, it will start to damage your tissues. So you can see that infrared has less energy, it doesn't damage your tissues. Ultraviolet light has more energy and does damage your tissues. Of all of these different wavelengths, there's a tiny sliver of wavelengths between about 380 nanometers to about 760-ish nanometers that we refer to as visible light, simply because the photoreceptors in our eyes are sensitive to these wavelengths. And when light, say, of 700 nanometers strikes those photoreceptors, your brain perceives that as being red. Whereas when light that's 400 nanometers strikes your photoreceptors, your brain perceives that as being blue. Now, it's interesting to note here that all living things that have eyes uh, are sensitive to the same wavelengths. There are some organisms that can see out into the UV and some that can see out into the infrared, but generally all things with eyes use the same visible light spectrum. Another cool thing is that plants, photosynthetic organisms, use the same tiny sliver of the electromagnetic spectrum to do photosynthesis. Why is it that plants use the same part of the spectrum as animals use for a very different process? Plants use it for photosynthesis, animals use it to see. Why just that one sliver out of all of these different wavelengths? I'll let you think about that. Another aspect of light is that it behaves as particles, and this is what's known as the wave-particle duality of light. When we measure or observe light in certain ways, it appears to be a wave, and when we observe light in other circumstances, it appears to behave as a particle. In some way, it is both a particle and a wave simultaneously, and I'm going to let your physics professors discuss that at greater length. The particles are referred to as photons, and they have no mass whatsoever. But they do carry energy, and how much energy a given photon carries depends on the wavelength of that photon. Remember that the longer wavelengths have lower energy, and the the shorter wavelengths have higher energy. So when we look at how light interacts with matter, light can be absorbed by matter. So if you have a photon of light of a specific energy, in other words, a specific wavelength photon, striking a specific atom, the electrons of that atom can absorb that energy. And in absorbing that energy, it moves that electron to a higher energy state, a more excited state. The photon itself is now gone. The energy that was that photon is now in that electron. This is the fundamental basis of photosynthesis, as you'll see later on in the semester. But it's important to us here because we're going to use the absorbance of how matter absorbs light in order to determine the concentration of that substance. Each different molecule or atom in a molecule absorbs a different type of or different length of light. So if we look at, for example, chlorophyll, okay, chlorophyll A is capable of absorbing photons at about 700 or 680 nanometers very well. So it has a high absorbance at that particular wavelength. So photons in the red are absorbed very well, but photons in the green aren't absorbed very well by chlorophyll A. If you get down here into the blues, chlorophyll A is absorbing pretty well these photons of this wavelength, um, and off into the ultraviolet. Chlorophyll B, on the other hand, has very, very similar molecule to chlorophyll A, just slightly different, and that difference means that only photons of different wavelengths can excite it. So it absorbs very well at a different blue, and it in fact absorbs um, wavelengths at about 470, 480, much better than chlorophyll A does. It also absorbs down here in the orangey range as well. So this is what we refer to as an absorption spectrum, and you can do this for any molecule, and this is just for the visible wavelengths because that's what's biologically relevant, but you could extend this out um, into the X-ray, ultraviolet and X-rays, and you could extend it to the right to include infrared light and radio waves. But this is the part of the spectrum that's biologically relevant. Each substance will typically have an absorption maximum, a wavelength that it is particularly good at absorbing. Chlorophyll A absorbs best in the reds, chlorophyll B absorbs best in the blues. That doesn't mean it doesn't absorb any other wavelength, it just means it's really good at those specific wavelengths. So let's take a look at our spectrophotometer. So this is the basic setup of any spectrophotometer. You have a light source here on the left, and that usually is going to shine white light. That's light that contains all of the wavelengths of the visible spectrum. It'll have a filter so that you can select exactly which wavelength of light you want to pass through that filter. It'll have a sample chamber, and then on the far side you'll have a sensor that registers how many photons of light are striking it. The first step in spectrophotometry and using the spec is to blank the spectrophotometer. And that's very much like using tare on a balance. So you'll have what's a vial. It's called a cuvette. That's the square vial here. It's called a cuvette. And in that cuvette, you'll put what's called a blank solution. Now, your blank solution could be pure water. Okay? Even pure water is going to absorb certain wavelengths of light. And so, in order to take into account how much light that blank solution is absorbing, you're going to blank the spectrophotometer. Okay? But if you're not going to use pure water in your experimental condition, let's say you have some sort of buffer, maybe a pH buffer or a salt buffer or both, you want everything in your blank solution that's going to be in your experimental solution except for that one molecule that you want to measure the absorbance of. To use the balance analogy, before you weigh your sodium chloride, you put your weigh boat on the balance. It settles out, let's say it's half a gram, then you hit tare, and now the balance says 0, and now everything you're weighing is just the sodium chloride. You want everything that's going to be in your experimental solution to be in your blank solution, except for that one substance that you want to measure the absorbance of. So let's dissolve something in the solution. Now you have your base solution, but now you have your solute of interest in here. And you'll see not every photon gets through that solution. Some of those photons are being absorbed by your solute. So fewer photons strike the sensor over here on the right. That means you've increased the absorbance above your blank solution. If we increase the concentration, even more photons get absorbed as they pass through your solution, and fewer photons hit the sensor. So it registers a higher absorbance. So already you can see now the concentration of your substance in that solution is directly related to how many photons strike that sensor. Or in other words, how much light is being absorbed by your solute is directly related to the concentration of that solute in solution. To put some math on this so we can get a specific concentration, we rely on Beer's law, which has nothing to do with the alcoholic beverage. This was developed by a guy named Beer, and it's a very simple equation where on the left you have A, which is absorbance. That's what we're going to measure with our spectrophotometer. And that is equal to something called the extinction coefficient, which we'll talk about in a second, times the length that the light has to pass through to get to the sensor. You can imagine that the farther the light has to pass through a substance, the more chances photons are going to get absorbed while traveling through that substance. So you have to know how far the light traveled through your substance. And then finally, concentration. And that's ultimately what we're going to be looking for. Now let's talk about that extinction coefficient a little bit. So extinction coefficients are unique to each different solute, and they have to be measured. This is something that's determined empirically, and they're specific to the substance, but also to the circumstances in which you're measuring the extinction coefficient. So which wavelength do you use to measure the extinction coefficient, as well as what pH you're measuring the extinction coefficient at, affects the extinction coefficient. And when you go to measure your substance, you need to use an extinction coefficient that had the same pH and use the same wavelength that you want to use in your experiment. Usually, the extinction coefficient is expressed in units like moles per liter. That's very, very common in chemistry, for example. In biology, it's more common for the extinction coefficient to be measured in milligrams per milliliter. Both are just different ways of expressing concentration. So if we look at how a solute absorbs a specific wavelength of light, so here we're measuring the absorption of a given substance at 600 nanometers. So we're shining 600 nanometer light, that's somewhere in the bluish range. You can see that as concentration increases, absorbance increases in a linear fashion. So for every little bit of concentration increase, you get a bit of absorbance increase, up to a point. And at that point, this starts to level off and you get into the curved portion. Once you get into the curved portion of this, you can no longer determine concentration based on absorbance. You can see that at this concentration is absorbing about as much light as at this concentration. The two absorbance is no longer indicative of that change in concentration from here to here. So you have to use the linear portion of this curve. So let's take an example of using Beer's equation or Beer's law for determining concentration. One of the things we'll do later in the semester when we do photosynthesis experiments is measure the concentration of chlorophyll in a solution. And we'll take that solution of chlorophyll and we'll measure the absorbance. I've looked up for you already. The extinction coefficient for chlorophyll happens to be 34. The path length for our spectrophotometers is exactly 1 centimeter, which is going to be handy in a minute. And then, of course, we want to know the concentration. So we solve this equation for C. So if you divide both sides of the equation by EL, you get A over EL equals C, or A over 34 times 1, our path length. That's what makes 1 centimeter particularly handy. So A over 34 equals our concentration. in milligrams per milliliter. That's what we'll ultimately be doing later on in the semester. Tomorrow we're just going to get used to using the spectrophotometers.